Hey AP Stats, our first section today is 6.2 and we're going to talk about the binomial probability distribution. So these are kind of the objectives I'd like to get out of it. All of this PowerPoint is on Blackboard, so if you miss something while I'm talking through it, go back, open it up, continue your notes. So an experiment is said to be binomial if the following things are true. There's a fixed number of trials. It happens a finite amount of times, maybe 20 times, 20 questions. The trials are independent. One question doesn't depend on the previous one, on an answer from the previous one. It's very independent. And there are two mutually exclusive outcomes, either a success or a failure. So think about taking a multiple choice test. There's 20 questions. All those questions are independent from each other, hopefully. And you either have the option of getting it right or wrong. Now, your chances for failure might be higher because if there's four multiple choice options, 3 of them are wrong and 1 of them is right. But there's only 2 options. You're either right or you're wrong. And then that idea that the probability of success is fixed for each trial of the experiment. There's not multiple successes per problem kind of thing. Okay? So some of the notation we use n for the number of trials. We wrote p for the probability of success. If p is the probability of success, then 1 minus p is the probability of failure. And then x, remember, is that random variable. Today we're going to use it for a binomial random variable that denotes the number of successes in an independent trial of the experiment. Remember, with those random variables, we like them to be between 0 and the number of trials in the experiment. If we have 20 trials, we can't have 21 random variables. So let's go through some of these. A player rolls a pair of fair dice 10 times, and the success is going to be when 7 is rolled. Okay? That's binomial. We have a fixed number of trials 10 times. We have a success and a failure, either 7 or not 7. So this next example says the 11th largest airlines had an on-time percentage of 84.7 in November 2001, according to some consumer report. We're assessing reasons for delays, and we randomly select flights until we find 10 that are not on time. Is that binomial or not? And the answer would be no, it's not a fixed number of trials. We're looking at, kind of a random sample of things, but we can't possibly quantify all the different airplane trials, especially since we're picking 10, or we're picking until we find 10 that are not on time. Are we picking 20 that are on time first, and then there's 10 that are not on time for a total of 30 trials? Or, are we going to find more that are on time since we have 84.7%? This third example, in a class of 30 students, 55% are female. The instructor randomly selects 4 students. The number X of females is recorded. Is that binomial or not? And again, not binomial, it's not independent. As I select one female, I have less and less students to pick from, and that's going to affect what percentage left are female. So if I have a 55% chance of picking the first one, that percentage should go down as I pick more students randomly. Okay? So if we were to kind of go back to that airline idea, the 11th largest air carrier had an on-time percentage, now we are saying 79% in May 2008. And we're going to select 4 random flights. That's 4 trials. And we're going to look at how many times they were actually on time. So we're looking at 4 flights, 4 trials, and they're either on time or they're a failure. Okay? And we're going to try to construct those probability distributions based on a tree diagram we're drawing. Remember that a probability distribution, you're listing all your outcomes, and then the probability that that outcome happens, they need to be decimal probabilities, and they add up to 1. Okay, and so we're going to go through and see kind of how we create that probability distribution from a binomial probability. So here's our tree diagram. Here it was on time, here it failed. And then from there, it has the idea of being on time or failing. And we're doing it for 4 trials, 4 flights. And we want to construct that probability distribution. So we're looking at the number of successes. We see it ranges from 4 to 0. So we'll start with the lowest one at 0 and see how many zeros we have. There's just one. And it failed, 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 failed. So we're looking at the probability of failure. Remember, we said the probability of success was 79%. So the probability of failure then is 21%. So the probability that all of them are not on time for 4 trials would be 0.21 times 0.21 times 0.21 times 0.21, which gives us this nice decimal. And we're going to go ahead and record that in our probability distribution chart. Then we do the same thing for the successes where only 1 flight was on time. Okay, and we see that it happens 4 times. The first time it was on time, so 79%, and then the other 3 were failures, so 0.21, 0.21, 0.21. This one here, it failed the first time, so 0.21, then it was a success, so 0.79. So you see that 0.79 just moves through to the first one was a success, the second one was a success, the third one was a success, the fourth one was a success. So that there's 1 success for every line, and the rest of them are failures. We add all those up, we get our probability that there is 1 success. We do the same thing for 2. We see that there are 6 2s. Each of those should have 2.79s and 2.21s. So if we did just this line and multiplied by 6, since we have 6 2s, that will give us this decimal down here. And again, we're recording these in our probability distribution charts as we go. We do the same thing for 3. There's 4 of them, so we do 3 successes, 1 failure, 3 successes, 1 failure, 3 successes, 1 failure, 1 failure, and 3 successes. Here's our probability that that happens. And then 4, 1, all on time, 4 successes. There's only 1 of those, so 0.79 times itself 4 times gives us this. And here's our probability distribution table. If you add all these up, of course, they add to 1. They're all between 0 and 1. So this is a good binomial probability distribution. We come up with a probability distribution function, which is given by this formula. You'll notice we have a combination in there. Remember, we can do that on our calculator. We have so we have the number of trials combination with the number of successes. Then we have the probability of the success raised to the number of successes we had times 1 minus p, the number of failures, to the n minus x. So the number of trials minus the number of successes. That's what we did here when we were adding these up. Okay, it's the same idea. It's just a formula that if you know how to use it, you can do it much quicker than having to draw a tree diagram and go through it for each number of successes. Okay, so we'll do an example that would use that. We have 35% of all car-owning households have 3 or more cars. Remember some of the stuff with greater than, less than, greater than or equal to, less than or equal to, because that'll change how some of these are written. So we have a random sample of 20 house-owning cars, so 20 trials, and we want the probability that exactly 5 have 3 or more cars. So what does that look like? 20 trials, combination 5 successes. The probability of a success we said was 35% raised to the 5th power, not 35%, so 1 minus that, to the 15th power, because that would be 15 failures. And this is our probability that we get. With that same idea in mind, seeing how we use those numbers in this formula, try part B. We have that same number of trials, but this time we want the probability that less than 4 have 3 or more cars. Think less than 4 is going to be the same idea as less than or equal to 3. So you might want to rewrite it first that way. If it's less than or equal to 3, we're going to have to find the probability of 0, probability of 1, probability of 2, and probability of 3. Use that formula and you'll get this answer. And finally, part C, the random sample, 20 cars, same number of trials. At least 4 have 3 or more cars. At least 4, we're going to start at 4 and then do the probability of 5, 6, 7, 8, 9, 10, 11, 12, all the way to 20. Or we could do 1 minus this number that we just got, because we're not including these 4 digits. We're including everything else, which gives us this 95, 96 almost %. Of course, we wanted to find the mean or expected value and the standard deviation of the binomial probability. Real easy formulas here. The mean is going to be the number of independent trials times the probability of success. The standard deviation is the square root of that times the failures. Okay, so number of successes times the probability of success times 1 minus the probability of success, which gives us that probability of failure. So again, we're looking at that automotive problem. 35% of households own 3 or more cars. This time we have a simple random sample of 400 car-owning households, and we're going to find the mean and standard deviations. So we're going to take 400 trials times the probability of success, which was 35%. That gives us 140. For the standard deviation, we do 400 times 0.35 times 1 minus 0.35. Square root of all that gives us that 9.54. And that's it for binomial probability, except for how this test of superciliousness relates. So stay tuned.